Assalamualaikum warahmatullahi wabarakatuh. Today we will learn on optical system design. Okay, now let us see on the overview of this chapter. So basically, in this chapter, you will design a point-to-point digital transmission link. Okay, and there are some issues that you need to consider. So these are the two issues. The first issue is on the link power budget calculations, and the second issue is on the link rise time budget calculations. So in order to ensure that your design is viable, you need to satisfy both the link power budget and also the link rise time budget. Okay, so let's see one of the most important performance parameter, which is on bit error rate or BER. So BER is actually the probability that an error will occur in a given bit period. Okay, it is given by this formula. BER equal to NE divided by NT. NE is actually the number of errors divided by NT. NT is actually the number of bits transmitted. Okay, number of errors divided by number of bits transmitted. Okay, so basically, the lower the BR, the better our system is. Okay, because our error is less. Okay, so for many applications, the maximum BR is equal to 10 to the power of negative 9, which means that one error will occur in every 10 to the power of 9 received bits. Okay, so that is what meant by BR equal to 10 to the power of negative 9. For telecommunication applications, the maximum BR usually is in the range of 10 to the power of negative 9 to 10 to the power of negative 12. Okay, now let us see on the key system requirement in order to design a point-to-point links. Okay, so in order to design an optical point-to-point link, first you need to know what is your desired transmission distance, the bit rate or the channel bandwidth of your system, and also you need to know what is your BER of the network. Okay, so in order to design a point-to-point link, first you need to know what is the optical transmitter that you will use. Either it is an LED or a laser, and the type of optical fiber that you want to use, either it is a multi-mode fiber or a single mode fiber, and finally, what is the type of optical receiver that you want to use, either it is a PIN or APD photodetector. If it is regarding on optical transmitter, you need to know what is your desired emission wavelength, the spectral width, the power, the effective radiating area, and also the emission pattern. For the optical fiber, you need to know what is the core size of your fiber, the core index profile, the bandwidth, the attenuation, and also the numerical aperture. And for the optical receiver, you need to know what is the optical receiver responsivity, the operating wavelength, the speed, and also the sensitivity of your receiver. Okay, so now let us see on the system considerations. First, is the system consideration in selecting the desired fiber. So in selecting the fiber, the most important major factor is actually the bit rate and the distance, because this will determine the type of fiber that you will use. Okay, so other factor that you need to consider is on the attenuation of the fiber. Okay, the bit rate distance product, you need to know what is your desired bit rate distance product, the cost of the source, connectors, splicers, your detectors, and many other components. And then, only then you can decide what is the type of fiber cable that you want to use. Either it is more suitable to use multi-mode or a single mode fiber, and whether you want to use a step index or a graded index fiber. Okay, now let us recall back what is bit rate distance product. So bit rate distance product is actually to know the capacity of an optical communication system. Okay, so basically the higher the capacity of the optical communication system, the higher the bit rate distance product is. Okay, So for example, if your system is capable to transmit 10 megabit per second over 1 kilometer, so it means that your bit rate distance product is 10 megabit per second kilometer. Okay, so 10 megabit per second multiply with 1 kilometer. Okay, so usually for 10 megabit per second kilometer, it is suitable for local area network, for the suitable bit rate distance product. Okay, so 10 megabit per second kilometer is actually equivalent to 100 megabit per second along 100 meter, 1 gigabit per second along 10 meter, 10 gigabit per second along 1 meter, 100 gigabit per second along 10 cm, 1 terabit per second along 1 centimeter. Okay, the shorter the distance is, the higher the bit rate. Okay. Okay, the second consideration is on selecting the optical source, whether you want to use an LED or a laser. So these are the parameters that you need to consider. The first one is on the emission wavelength. Okay, at what wavelength your system is operating. Okay, the spectral line width or the full width half maximum. Okay, so FWHM, full width half maximum, is actually the width of your source, your optical source. So in this case, your width of your source when your amplitude is dropped into half. Okay, so this is your FWHM. And then you also need to determine what is your optical source output power, the stability, the emission pattern. For example, this is the emission pattern of an LED, and this is the emission pattern of the laser. And finally, the effective radiating area. Okay, so this is the graph of fiber attenuation versus the wavelength. Okay, basically, the lower the attenuation, the better your fiber is. Okay, so you can see here, in early 1970s, they have picked the first window. Okay, because at this time, at this particular window, it has the lowest attenuation. Okay, they have different types of different material of fiber, so that's how they get this graph, the fiber attenuation graph. Okay, in 1980s and 1990s, this is how actually the look of the fiber attenuation, and at lowest attenuation, they pick the window. So this is the second window, and this is the third window that is still being used until today. Okay, now let us look on the criteria on selecting the photo detector. So as you know that there are a few types of photo detectors. The most popular one is on APD and also pin photo detector. APD, it has higher sensitivity, but it is more complex. It needs high bias voltage, 40 volt and above, and it is more expensive. For pin photo detector, it is simpler, thermally stable, it needs low bias voltage, 5 volt or less, and it is less expensive. So you need to determine whether you have to use APD or pin photo detector for your network or for your link. Okay, so other than that, you also need to know what is the responsivity of your photo detector. Okay, so revise back. What is responsivity? Responsivity is actually the ratio of output current to the input optical power. Okay, the ratio of output current of the detector to the input optical power. Okay, so that's the definition of responsivity. Okay, other than that, you should know on the operating wavelength of your photodetector and its spectral selectivity, the speed, and also the photosensitive area, and finally the sensitivity of your photodetector. Okay, so this is actually the table of typical bit rate at different wavelengths. So you can see here, for wavelength from 800 to 900 nanometer, typically we will use multimode fiber. For LED, the bit rate distance product is 150 megabit per second, but for laser it is higher. It is 2500 megabit per second kilometer. For 1300 nanometer, whereas at this wavelength, it has the lowest dispersion. Okay, for LED, this is the bit rate distance product, but for laser system, the bitrate distance product is much greater, right? Which is 25 gigabit per second kilometer. Okay, for 1550 nanometer, this is the lowest attenuation. Okay, so again for LED, the bitrate distance product is lower as compared to the laser system. Okay, so let us see on system design considerations. So basically, you should consider these two types of budget in your design. The first one is link power budget and also the rise time budget. Okay, why we need link power budget? So link power budget is needed to ensure that there is enough power margin in the system to meet the given bit error rate. Okay, so that's why we need to calculate the link power budget. Okay, another consideration is on rise time budget. Okay, so rise time budget is actually to ensure each element of the link is fast enough to meet the given bit rate. Okay, so these are the system design considerations. Okay, so this is the graph of receiver sensitivity versus the data rate. Okay, so you can see here, the higher the receiver sensitivity, the higher the data rate. Okay, so this is for pin photodetector at this specific wavelength. This is for APD, for pin photodetector at 1300 nanometer. Okay, and this is the receiver sensitivity for APD at 1550 nanometer. Okay, now let us look on optical power loss model for a point-to-point link. Okay, so in this figure, we can see that we have a transmitter, we have the connectors, we have the splicers along this fiber, and also an optical receiver. Okay, so in this model, we can actually calculate the total loss. So total loss equal to power source. Okay, power source is actually the transmitted power. Okay, minus power received. PR is power received or the receiver sensitivity. Okay, so total loss equal to, so this is actually the connector loss plus with the splices loss plus with the fiber attenuation plus with the system margin. So you will see later what is actually system margin in the following slides. Okay, another formula that I would like to introduce in order to ensure whether your system is viable or not is PM. PM is power margin. Okay, for a system to be viable, your power margin must be greater than 0. Okay, so if your power margin is less than 0, then your system or your design is not viable. Okay, so your power margin, the equation for power margin is given by this equation. So power margin equal to power source minus power received minus the connector loss minus the splices loss minus the fiber attenuation minus the system margin. Okay, so please use this formula in order to ensure whether your design or your link is viable or not. Okay, now let us look on safety margin. Safety margin is actually a loss allocation used to allow for component aging, temperature fluctuation, and losses arising from components that might be added in the future. Okay, the typical value is between 5 to 10 dB.